I'm now presenting you a third problem. By this time, I hope you have understood the overall mechanism, how to think. That's very, very important. Essentially, I've selected problems so far where the integration does not get triggered. So let us analyze this problem with respect to that principle and then see how a change of order of integration can really be useful. The problem is on board. Integration of some variable from 0 to 2 log root 3. It's a natural log. Then y by 2 to square root of log 3 e power x square dx dy. Study the inner limits, they are functions of y. So the order dx dy is okay, which means that these limits correspond to an R y region. So these should be y limits. Y is equal to 0 to y is equal to twice square root of log 3. These are the x limits. X is equal to y by 2. X is equal to square root of log 3. Don't panic. Log 3 is after all a real number. So twice square root of log 3 is some number. Similarly, this is some number. So they are constants. So let's try to put them on a graph. Beginning with y is equal to 0, which corresponds to the x-axis. I draw another line parallel to the x-axis. So many units above the x-axis, 2 square root of log 3. Don't worry what's the numerical value, but it must be some positive number. So this is y is equal to 2 square root of log 3. So in this horizontal frame, let us see what are the other equations. X is equal to y by 2 can be seen as y is equal to 2x. That means it's a line passing through the origin, which may appear like this. So I'll write x is equal to y by 2 there. And then the immediate thing you have to do is find the point of intersection. So you have to solve these two equations to get that point. That looks very simple. You replace the y here with 2 square root of log 3. 2 square root of log 3 divided by 2 will give you x is equal to log 3. So this point will have an x coordinate square root of log 3 with this as a y coordinate, 2 square root of log 3. I hope you're all able to understand. We just solve them and it's a very simple situation. So now where are we? We have plotted this, we have plotted this, we have plotted this. Now this remains. X is equal to constant should be a line parallel to the y-axis. But where do you draw it? Can I draw it through this point? Yes, because it matches with the x coordinate there. So this is x is equal to square root of log. So let's number one by one. Y is equal to 0. That is where we started from. Y is equal to twice square root of log 3 number 2. X is equal to y by 3 is number 3. X is equal to square root of log 3 is number 4. So obviously this is the region of integration, which is originally R1. Having done this, the next focus is go and look at the function. Was this all necessary at all? If we are not doing all this and we are able to integrate directly, then no, you don't need all this fuss. But you can see e power x squared cannot be integrated with respect to x. Therefore, I have decided to change the order of integration. So I'm now going to redraw this diagram. To express it as an Rx region. Begin with the corner points. So you just have to copy most of them from that original diagram. And let's try to figure out the limits now. We are trying to see this as an Rx region. So we are fixing it within the vertical frame. So with this as the left vertical, this as the right vertical. This is the lower curve with equation y is equal to 0. And this is the upper curve whose equation can be derived from here as y is equal to 2x. So this is 3 and that is 4. 1, 2, 3, 4. Shade the region. Label it as Rx. So the whole details are on the board. And now I'm going to write how the problem looks after changing the order of integration. So let me copy the original integral here. 0 to y square root of log 3. Then y by 2 to square root of log 3. The function is e power x squared dx dy. This was tough, but let's see if this can help us. 0 to square root of log 3. 0 to x e power x squared order dy dx. Original transform. Now this, of course, this is untouchable. We cannot do anything. Let's hope we can integrate that. And it looks promising because e power x square remains constant with respect to y. So I can trigger the integration. So I'm not going to show you how to evaluate this right hand side double integral to get the output. So now let's look at the final stages of the problem. Now that the order has been understood after changing it. So let's finish the evaluation also. You can see the right hand side has been copied, and then I'm going to integrate this function with respect to y. That's alright because e power x square remains a constant with respect to y, and I get 0 to square root of log 3 e power x square times y. Limits are 0 to 2x dx. So 0 to square root of log 3 e power x square times 2x minus 0 dx. That's very good because the differential of x square is directly available here. So the integration of an exponential function under these conditions will be just e power x squared from 0 to square root of 3. So that will make it e power square root of log 3 square minus e power 0. This is e power log 3 minus e power 0. E power log 3 is 3 minus e power 0 is 1. That makes it 2. So e power log 3 is 3 is a well-known principle. However, for the benefit of students who are new to this part of math, I can just put up a small box for you here. E raised to log theta is theta. E raised to minus log theta is 1 upon theta. E raised to k log theta is theta raised to k, and e power minus k log theta is 1 upon theta power k. This can be useful in some problems where these situations of exponentials and logarithms coming together. So this is my third example. And is there something else to learn? Yes, you should now wait for my next example. I have chosen this example for a specific reason. It is a problem where the inner limits are functions of x, and then obviously corresponding to an Rx region. Integration really not very difficult because it's after all a dy dx integration with a function assumed to be 1. So I'm not worried about the integration process, but in case we'll have to change the order of integration for such a problem, what are the complexities that lie? So let us analyze the region first. Inner limits functions of x and the order dy dx is okay, and these limits correspond to an Rx region with these are the x limits. These are the lower limits in that order. And I would like to see this on the graph. Beginning with x is equal to 0, which corresponds to the y-axis, to x is equal to 1, which is 1 unit parallel to the y-axis to the right. Then y is equal to x squared is a vertical parabola. Let me write the equation there. Before doing anything, I'll just find this intersection point where x is equal to 1, which you can copy from here, derive y from here, y is equal to 1 square, which is also 1. So let us see what happened so far. This has been plotted, x is equal to 0. This has been plotted, x is equal to 1. Y is equal to x squared has been plotted. Now comes y is equal to 2 minus x. So this would be y is equal to 2 minus x is the same as x plus y is equal to 2. Seen in the intercept form, it looks like this. That means this is a line having intercepts 2 and 2 on the x and y axis. So 2 units on the y axis. So let me extend the x axis to that level. Let me also extend the y axis to accommodate that line. So just for the sake of completing the figure, this point is 2, 0. This point is 0, 2. Now our interest is the region between x is equal to 0 to x is equal to 1. That's number 1 to 2. Y is equal to x square is number 3. And y is equal to 2 minus x is number 4. So that's the region of integration. So let's look at the region by itself. The focus of this problem is on the region. It's not so simple to handle this particular region if the function that we have to integrate was tough. However, there is no complexity in terms of integration. That's not the point. The point is, in case a tough function would have come with these types of regions, definitely you'll have to think carefully. So this Rx region, I would like to see as Ry. So I'm going to redraw the diagram with only the essential parts. I'll do that. I will do this, and I'm not interested in this extended line. I'm not interested anything else, only this is the region. Okay, I just copied it, and then I'll mark the corner points 1 1 0 2 0 0, and I'll try to see this region within horizontal lines drawn at the extreme bottom and extreme top. When I do this, I find there is one point of intersection which is not allowing me to write this as a single array region. So I split the region here into two parts. So what I'm actually teaching in this problem is region segmentation. So I've segmented into two parts. Let's call this part A, let's call this part B. For the sake of better visualization, let me shade this with vertical bars. Let me shade this with horizontal bars. And let us also plot, rather mark this point. Its coordinates will be 0, 1. I think all the corner points are now there. And then I want to express A as an RY region, and I want to express B also as an RY region. So only focus on A now. I want to see it as an RY region between these two horizontals. So I have to set up my equations. This of course is y is equal to 0. This is y is equal to 1 because the y coordinates of this horizontal line are y is equal to 1. So let's call it 1, 2. Then this is x is equal to 0, and this is x is equal to square root of y. Coming from y is equal to x squared, write x as a function of y and you get that. So continuing the numbering, this would be 3, that would be 4. So let's fill up this box. Y is equal to 0 to y is equal to 1. X is equal to 0 to x is equal to square root of 5. B is an extended portion of the diagonal above A. And then I want to see this region also as an RY region. So I'll have to see it within horizontal lines. This is the lower horizontal line and the upper horizontal line. This lower horizontal line already has been fixed as the equation y is equal to 1. So I'll call this 1 now. This will be y is equal to 2. This is the left boundary, which is the same as the left boundary of the lower region, x is equal to 0. But careful about this. This is the slant line, so the equation is here, but put it as x written in terms of y. So x is equal to 2 minus 1. So if this is 1, this is 2, this will be 3, and that will be 4. So I will now fill up this box. Starting from y is equal to 1 to y is equal to 2, 1 to 2, then x is equal to 0 to x is equal to 2. Having done this, I think we can now express the original integral as the sum of two new double integrals. How does it look like? So let me copy the original integral on the left hand side. 0 to 1 x squared to 2 minus x dy dx is identically equal to 0 to 1 0 to square root of y. Change the order to dx dy plus integral 1 to 2 0 to 2 minus y dx dy. Strictly speaking, this problem does not warrant a change of order of integration. But in case you land into a situation where the region has to be split, this is how you think. So the evaluation is pretty straightforward. I will do one of them just for the sake of interest, and the other can be taken up by you. I will do this one. I will call this integral as I1. I will call that as I2. The evaluation of I1 will be 0 to 1. The integration of dx is x. Apply the limits 0 to square root of y dy. So you get square root of y times dy, which is the same as 0 to 1 y raised to half dy. Integrate that function, you get y power half plus 1 by half plus 1 from 0 to 1. So this would be y raised to 3 by 2, right, by 2 from 0 to 1. So that would make it 2 by 3 times 1 minus 0, and the output is 2 by 3. So I1 gives us this output. What output I2 gives, you just find out because it's similar. And then finally, you can wind up the problem saying I is equal to I1 plus I2, where I1 is 2 by 3 and I2, you just fill it up and then you produce the answer. So this problem should explain or should help you understand how you must think of splitting or segmenting a region whenever necessary. So with these 4 problems, you must have learned quite a bit about the context in which the order of integration changes, how to go about it, but don't forget, you must be extremely good in the coordinate geometry of 2 dimensions. At least the famous curves you must be able to plot, and then the region analysis, how to understand an Rx region, how to understand an R1 region, and then the rest will be very, very straightforward. So let's move forward to the next topic.